Hello everyone, to the final part of paragraph 7.3, the product sum method. Well, we're not really going to discuss the product sum method that much today. We're going to take a look at proofs in mathematics. And to discuss what that is, I've started with this small strip here. You can see that proving something in mathematics is different than proving something in physics, for example. In mathematics, you have to prove why something is mathematically true. The very basics, you could say, you have to prove. You cannot say, yeah, well, mathematics say this is true. No, you have to prove that part is true. Well, if you're going to prove something for your physics teacher, maybe in a few years, well, you don't have to use half a piece of paper to prove that mathematics has proved something. You can just say, hey, well, that mathematic guy has proved this, so I'm going to use it. We're going to take a look at the first step. We're going to take a look at proving pure raw mathematics. Why is something mathematically true? I've also shared a video about this on YouTube. It's about making sense of irrational numbers. I'm not going to show it here in this video. I've shared a link in the Word document as well. Click it. I think it's rather fun and it introduces you to proving things about irrational numbers. We're going to take a look at how the book tackles this. So, theory C, proof with variables. There are two things that I want to make very clear, and that's that you can use these two pieces of information right here. You don't have to prove that. So, we know that every even number can be written as 2 times n, 2n, with n being any number, right? And every odd number can be written as 2n plus 1, right? So just change n into any whole number and you always get an odd number after that. For example, if n is 3, 2 times 3 is 6, yeah, that's an even number. 2 times 3 plus 1 is 7, hey, that's an odd number. You can use this information, right? They show you a few examples here in this box as well. Doesn't matter which number you take for n, you always find an odd number. So this is a very basic form to describe every odd number there is. And this is a very basic way to describe every even number there is. Well, we're going to use this to now prove different things, right? Before I'm going to show you that, the theory also says that all multiples of 4 can be written as 4 times n, and all multiples of 5 as 5 times n, etc. We're going to see that occur in a few exercises as well. They use n. You can also use another letter. You can use a, you can use p, you can use x, etc. K and l are often used as well. So it doesn't matter which number you use, or which letter you use, right? Let's take a look at how we can prove, for example, this theorem. The product of two odd numbers is always an odd number. Right. Let's just try it. Let's take two odd numbers, 3 and 5. 3 times 5 is 15. Hey, that's odd again. Hey, that's true indeed. Two other odd numbers, 3 and 7. 3 times 7 is 21. So, okay, I think this is indeed true. Let's prove it. How can you prove this? Well, we have to now discuss how we can write down this product of two numbers mathematically using numbers and letters. Let's take a look at the first odd number. We don't know which odd number we use, so we're going to describe it like this. Let's name this number A. That's the first odd number. Can be 1, can be 3, can be 21, 33, etc. But we can describe this number very basically by saying, well, this number, A, is equal to 2k plus 1. And they see that the book now uses the letter k. Could also use n, could also use a. They use k. Well, I also want to describe the second odd number. Let's call that second odd number b. And I'm going to describe that using b equals 2n plus 1. What is important is that you use two different letters here. You can say that b is also 2k plus 1, because then those a and b are always the same, and they don't have to be. The product of two odd numbers can be 3 and 3, or 5 and 5, but they can also be 3 and 7. or 3 and, for example, 9. So you can say 2k plus 1 and 2k plus 1. You must use a different letter here. 2k plus 1, 2n plus 1. Or 2k plus 1, 2l plus 1. Doesn't matter. Hey, so now we can say that a times b, the product of those two odd numbers, is going to be 2k plus 1 times 2n plus 1. Hey, this we can now work out if we want to. We can multiply out the brackets using the parrot's beak methods. Let's do that. You will find 2k times 2n is 4kn, 2k times 1 is 2k, 1 times 2n is 2n, and 1 times 1 is 1. And then you find this strange combination of terms right here, and you think, well, I cannot do anything with this. How can I use this to prove that this apparent string of terms is always going to be odd? Well, you can, but you have to use a trick for that. The trick that you're going to use is that we're now going to rewrite this as something inside of brackets again. How are we going to do that? Well, I want to now rewrite this to this basic form 2n plus 1 again. Well, not 2n because I have n here. Let's say 2a plus 1. So I'm quite happy that I have a 1 here. I want that 1 to be here. But this part, 4kn plus 2k plus 2n, I wish that was, for example, 2a or 2b or 2c, 2d, something like this. Can we rewrite this in a certain way? Yes, we can. Because what is the common factor between those three terms? If you do this correctly, you will find that the only common factor here is 2. So we can rewrite this as 2 times 2k n plus k plus n. This becomes 4kn, that's this part. 2k is here, 2n is here. And I'll leave this plus 1 outside of my brackets because I want it to be there. Why? Well, take a look at everything inside of the brackets. 2kn plus k plus n. You're going to do something very peculiar here. You say, well, all those things together are going to be a number again, right? So if it's going to be any number, I don't care if it's odd or an even number, it's going to be a number. I can say, well, 2kn plus k plus n is going to be the same as the letter, for example, p, any natural number p. So I can now substitute p for 2kn plus k plus n. Why would I do that? Well, because then we are done. Then I get 2p plus 1. Oh, but that's the same as 2n plus 1, right? So this means that a times b can be written to the form 2p plus 1. And that means that a times b is always going to be odd. Try it. Fill in any number for p. Make it as big as you want to. It's always going to give me an odd number, and thus a times b is also odd. This particular way of proving things, in my personal experience, is quite abstract for a lot of you. So I'm going to make a separate video where I will try and give you a few more examples on how you can prove things using this method. Try to watch those videos if you find this difficult as well, because there is not a video of the Wiskunde Academy about this part. So I will try to explain a few more exercises in another video.